Hello guys, so welcome back to our lecture 15. This is the last part of this lecture and also the last part in the diode study, you know. So in this recording we're gonna explore another special diode, which is basically the light emitting diode, LED. And as the name suggests, this diode emits light, okay, when it's forward bias. So with a proper biasing, which is basically forward bias, and a proper current, okay, this diode can emit light, which is very useful in many applications. Okay, as you see here, it can emit light with different, colors: white light, red, blue, different kind of light you can get. You can even get ultraviolet light. I mean, lights that you cannot see, or even infrared light, which basically is the one in your cameras. Okay, so basically you can, get not just visible light, but you can get even, non-visible light, like for example, infrared or ultraviolet. Okay, here is a symbol for it. It's very, simple symbol, basically, because it's just a normal diode with these two arrows to get with these two arrows to show you that it emits light. Okay. So how this happens? Okay, it's basically based on the energy band diagram. If we go back to the energy band diagram that we discussed, in our first lectures about the diode or semiconductor in general, we said that there is valence band and conduction band. Okay, and in valence band we usually have holes, and in conduction band we usually have electrons. Good. When electron move from the valence band to the conduction band, okay, when it goes to the conduction band, it has what's called lifetime. So basically, this lifetime is the average time that the electron will stay there in the conduction band before it goes back to the valence band. Okay, so when it goes back to the valence band after this lifetime, we can say, so what happened is that this operation of recombining, we can say recombine, and I mean by recombining of the electron with its hole or with a hole. So this combination process result in some energy. So there will be energy as a result of this process. Okay. Energy has many forms. It can be heat. It can be electromagnetic wave. Electromagnetic wave. Okay. In silicon, it was just heat. So this recombination process must, show as a form of heat, increase in temperature of the silicon. But for other semiconductor types, like for example, gallium arsenide, okay, this is another semiconductor. This energy is basically visible. You can see it. Like for example, red light or blue light, green light, okay? And why is that? Because basically this energy is equal to the difference between EC or EV, or basically EG. We said that this energy gap has a certain energy. Okay, so this energy basically that the electron emits when it recombines with the hole is basically equal to EG. Okay, and this energy equal to HF. H is constant, and the F now is the frequency of the electromagnetic wave. And if this frequency is equal to one of the frequencies of the light that we know about. I mean, the white light, or the red light or the blue light, then we can have different light emitted after the recombination process. Okay, so if we control EG, this difference between the energy, the conduction band and the valence band, if we can control it, okay, then we can produce different HFs, okay, and for the, if we want, for example, blue, then we know the frequency of the blue, then we multiply it by H. This will give us the required energy gap, so we can engineer the material so that the recombination process will end up with emitting this blue light, okay, or whatever light we want. So that's basically how the the light emitting diode works, okay. And as we said, it has many applications. For example, the LED bulbs that you have in your home, okay. Also the 7-segment display, which is basically used in many calculators till this moment. There are smart watches that use still LED because it's really shiny. I mean, it gives you a better better displays than the normal LCD watches, okay, or even of course in in your designs projects. So I'm gonna explain a little bit about this 7-segment displays because they are really nice and really interesting. So basically this 7-segment display is just 7 segment, 7 LEDs, okay. So you have 7 LEDs like this, and sometimes you have this display decimal point, I'm sorry. So you have 8 8 LEDs, but it's common to say about it or name it 7-segment. Also, as I said, you might have this decimal display with decimal point LED, which will be the 8 LED, okay. So basically it is something like this. You have the 7 LEDs connected like this, okay. They might have the same anode. I mean, all the bees are connected together, or they might, and in that case it's called the common anode. And of course, to make them light, I mean give light, this should be connected to the high the high voltage. And they might be common cathode as well. I mean, there are 7 segments that are common cathode. I mean, all the ends are connected to the same to the same volt or shorted, just like this, just like the common anode here, okay. So let's take the common anode as an example. So basically, to control which will give light and which will not light, you just control here these inputs here, this one or this one or this one, which is basically A, B, C, D, E, until you reach the decimal point, okay. So any one of those, for example A, connected to ground, then there is a path between the VCC and the ground, then there will be a current, so you will have a light out of A. If it's open circuit, not connected to ground, I mean, then there will be open circuit, so the current will not flow, so basically you will not have a light out of this segment or this LED. For each LED, there is what's called minimum current. And this is basically the minimum forward current that you can, that makes the light out of the LED visible. So not just any forward bias can work in this. The LED might be forward, but the amount of current is low, so you will not see the light clearly, we can say. So there might be enough amount of current that flows into the LED so that you can see the light. Another aspect of design is the maximum current now in each LED. So, okay, now we need high current, greater than the minimum current so that we can see the light. But how much Can we just put any current higher than the minimum current? No. There is also maximum rating, maximum power that this diode can handle. So you should check the data sheet of this LED so to know what is the maximum current. So basically the current that flows into the LED should be between I minimum and I maximum. So basically I forward should be greater than or equal to I forward minimum and less than or equal to I forward maximum. If you decrease than I forward minimum, you will not see the light. Although the diode is forward and conducting, I mean on. And if the current is higher than I maximum, the diode will break, will burn, basically. So we can control that based on the value of the resistor. This resistor is here. Okay. So basically, we can choose the resistor such that the current that will flow will be higher than IF minimum and less than IF maximum. Let's take an example. So here is a LED. Here is connected to what's called VCC. We will know what is why we call this high voltage VCC or this battery VCC when we study, you know, transistors just in the next lecture. So just, you know, call it VCC for now. 5 volt, for example. Here is R, and here is the ground. And this LED has VD on, for example, 1.5 volt. And usually the forward voltage, the built-in voltage of these LEDs usually high, 0.7 like silicon. It may be 2 volt, 3 volt even. Okay. So, and let's say that IF minimum is 1 milliampere and IF maximum is let's say 5 milliamperes. So let's design R, I mean choose R such that so let's choose R such that I forward higher than IF minimum and lower than IF maximum. Okay, so if the current flowing is IF minimum, this let's first, you know, determine the current as just the equation. So I is flowing in R, so it's equal to this point minus this point over R. So this point is basically, if you have here 5 volt and here is 1.5 volts, so this point is 5 minus 1.5. So this is 5 minus 1.5, which is basically 3.5. So 3.5 minus 0 over R. This should be, if this is just call it IF. So IF minimum, that means this will be maximum. So this will be 1 milliampere. And IF maximum, that means R minimum. 3.5 minus 0 equal to 5 milliampere. So basically, for IF to be greater than IF minimum and lower than IF maximum, that means R should be greater than R minimum and less than R maximum. So let's determine R min or R max. So from here, R max equal to 3.5 kilo ohm. And from here, we can determine R minimum. It would be 3.5 over 5 kilo ohm. Basically, it's less than 3.5 because it's divided by 5. It would be basically maybe 0.7. Oh, let's just ignore. Okay. So we can choose R with any value between, you know, 3.5 and 3.5 over 5. Okay. This will be 0.7 kilo ohms. So if we choose, for example, R equal to 1 kilo ohm, that will result in a current. Let's check this current. IF equal to 3.5 minus 0 over 1, which is 3.5 milliamperes. And that's basically higher than 1 milliampere and less than 5 milliamperes. Okay, good. That's for the R. The final aspect of the design here is the maximum power drained from the battery, VCC. So you have here a battery, and we said that we need enough current so we can clearly see the light out of this LED. So that means, and usually this current is high. Okay, so that will lead to that this will drain your battery faster, and this is a practical problem. It happened for me myself. So we need also to determine the maximum power. So the maximum power from the battery happen when all of them is on. And in this case, the digit will be 8. So when we display digit 8. So all of them will be on. Okay. So to determine the maximum power, you just need to know the current flowing in each diode, then multiply and then add them together. Okay, you will have 7 multiplied by whatever current is, and this will be the current that goes out of the battery. To determine the power of the battery at that time, it will be 8 multiplied by the battery voltage. So for I forward equal to 3.5 milliamperes, the one that we just determined right now based on our design or our choice for the resistor to be 1 kilo ohm. Okay, so the total current from the battery, basically that one here. So here you have 3.5 milliampere, again here 3.5 milliampere, until look, you can include the decimal point or not. Okay, but for our example, I will exclude the decimal point. I will just talk about the normal, most famous this 7-segment display, just the name 7, not 8. Okay, so at that case you have 7 multiplied by, so the total current here is 7 multiplied by 3.5 milliampere equal to 3.5 milliampere. Okay, so if we multiply, let's do that. This will be 24.5 milli. So the maximum power equal to the battery voltage. Let's assume the battery voltage is 5. We have it here 5. Not assume. Multiplied by 24.5 milli. So let's do that. This will be 122.5 milliwatts. Okay. So that's basically the maximum power that your circuit will drain out of the battery. Okay. The minimum power, of course, happens when you just have the minimum number of LEDs that can light at the same time. And of course, this will not happen when you have 0. No, because if you have 0, Okay, this means A, B, C, D, E, F are all, lighting. But this basically will happen when you have digit one, because in digit one you have either B or C, or I'm sorry, B and C, or F and E. Okay, either one of these sets. But basically you will have two segments lighting. So at 8 you have the maximum power drained. At digit one, not 0, you will have the minimum power. But we don't care about the minimum power. We always care about the maximum power. Okay, guys. So this is basically, how light emitting diode works, and how we can use them and design a circuit with 7-segment display like this. This concludes our discussion about diodes in general. Thank you very much for watching this, and see you in the next lecture. Bye-bye.